Hello. Okay, so let's get started. What I want to do today is start off by taking questions on the project. There may still be some. It's due tomorrow. And the second thing I want to do is use this time to kind of wrap up, or hopefully wrap up, our discussion of file systems. We might have a little bit more, but to sort of make progress. So first of all, questions.
So for RAID 5, is the choice of determining which parity layer it's on always from top left to bottom right?
Yes, I wanted to specify, make it sort of predictable for everybody's implementation exactly which disk would be the parity disk. Yes.
So when we want to compute the parity, do we have to read the previous stored information for this row or something like that?
So if when you are doing a write of a single block, you have to read some information to compute parity. If you're doing subtractive parity, then you need to read the old parity and the old value of that data block. If you're doing additive parity, you need to read all of the old data blocks. And then you need to write the new, in both cases, you need to write the new data block and the new parity block. The only requirement is that if you're doing a full stripe write, then you shouldn't read anything in advance. Because you shouldn't, when you're doing a full stripe write, you have all the data in memory to compute parity, and you don't need to read anything to do that. Other than that, it's up to you if you do additive or subtractive parity.
So if we are expected to write a full script, we need to first compute the parity, then write that in.
Yes. So you need to compute the parity if you're writing a full stripe.
We write, and read.
Correct.
Okay.
Yes.
So just to be clear, when we do like the recover from the script,
Yes.
we zero the disk.
So because of the confusion about zeroing the disk, I put up new code yesterday that will zero the disk for you. When you say disk array recover disk, it'll zero the disk for you automatically. So you don't need to zero the disk anymore.
Okay, and then
So if you wrote that code already, there's this nice little comment feature you can use to just put comments on the top and bottom of your code. So hopefully it's a minor change. And I apologize for changing it. It just seemed like for most people it would make it easier to put this into the baseline code.
yeah, and then after that, if like that disk was previously lost, do we like put the data on it? That's
Yes. So during the processing of the recover command, you should put all of the correct data back onto that disk. Yes.
When you remove the virtual disk files,
Do you need to?
remove the virtual disk
You do not, because they will be, the new code will zero them out when you start up. Yes.
In RAID 10, should you check that that the mirror and the original disk have the same that you read? That they're the
So
same?
when you're doing RAID 10 on a read, you only need to read from one of the two disks.
Okay, so
you
you
don't
don't
need
have
to
to
read from both. So there's no, in RAID, you don't need to detect errors. The way that errors are detected in these RAID systems is that the disk tells you that it's failed.
The disk failed.
Yes, and so there's no, standard RAID does nothing if a disk fails in some way other than
Okay.
turning itself off. If it fails by returning bad data, RAID doesn't help at all. So that is one thing hopefully you're learning by this, is that RAID does nothing to prevent, corrupting your data on disk.
Okay.
It just says if a whole disk fails, you can recover all that data. Yes?
it is possible at any time there are two or more than two failed disks.
Yes, so if you look at the script that Colin sent out, it's only about 10 lines long, and it fails two disks and sees what happens.
Two is most, or there will be more.
It could be more. It could be, all but one disk or all disks. Yes.
If we fail multiple disks like that, and then we recover one of them, do we just want to keep it with zeros in it? Because obviously we can't recompute what was really there.
Yes, if you can't recover what the value is, just leave it as zeros. And then,
But then if we recover the other disk, then we're just going to compute wrong parity.
Correct.
Okay.
correct. So if you have multiple disk failures, again, what you're learning is you will have corrupt data, and you won't really know that you have corrupt data. Any other questions? Yes, Koshik.
For RAID 5, I assume that your parity is supposed to be in strip seconds and not one block per disk going across disks?
Yes, parity is in strips. Because if you write, so I see, so you're saying we could have one parity block for all of the blocks, or we could have a parity strip for all the disks.
No, I mean, you could have parity blocks at one third of the strip sizes in each disk, or you could have parity blocks going as one block per disk, striping across the disks, irrespective of the stripe size.
So think about what the problem with having parity as one block per disk is. What that means that if your strip is size 2 and you lose the parity disk, you'll lose the parity and a data block. Without that data block, let me think. I guess you have all the other data blocks still, but you can't recompute that data block anymore because you don't have the parity. So you can't recover in that case.
You could, because you only lost one disk.
No, but if a disk holds parity and data.
No, not the same block. The parity is across blocks.
No, but suppose we have. Is this what you're suggesting? So this is blocks 1, 2, 3, 4, 5, 6, 7, and a parity block.
Yes, for those blocks.
Yes. So the question is, if we lose this disk, how do we ever get block 7 back? Right? If we lost this,
because the parity for.
But we lost the parity is on this disk also.
No, that's not what I meant. Actually,
Oh.
I'm sorry. So 1 is going to be block 0, 3 is going to be block 0, 5 is going to be block 0, and 7 is going to be block 0. And you're going to have one disk before that has parity to that block. Or you could say.
Wait. So this.
So that is going to be parity.
Okay, let me draw
You have
this.
2 blocks for parity on 2 different disks.
Yeah.
So you're going to have parity here,
0, block 0.
0 and parity.
No.
Oh, I see what you mean. So you're going to have 0, 1. So you might have 0 and then 1 parity and then 2, 3, 4, 5, something like this. So you have 2 separate parity blocks in a stripe that are on different disks. So this parity protects something like this.
No, that's not what I meant.
No. What did you mean?
I meant block 0 on disk 0 is going to be parity block.
Okay, we put parity here.
Block
What
1
goes here?
on disk 0 is going to be data 0.
Okay.
Block 0 on disk 1 is going to be data 0. And next one's going to be 1. No, not there. Next disk is going to have 1. Next disk is going to have 2. And the next block on disk 0 is going to have data 3. And then you're going to have parity.
Oh, I
You're gonna
see.
have 4.
So what you're really saying is, I think you could also draw this by saying,
Yes.
so this is not what you should do. This is just, because the thing is, when you have sequential writes, when you have sequential reads now, you can't read you can't read 2 blocks sequentially now from the same disk. You have to read from 2 disks. And the strip size really relates also to being sequential. And so you want to have parity, 0, 1, 2, 3, 4, 5. Okay, other questions?
You would have 6, 7 parity, right?
Yes.
And so on. Okay.
Yeah.
So in this case, means the strip is 2, right?
Yes, the strip is 2 here. Yes. Any other questions? Okay, so at the end of lecture, and I have this laptop here, I think I may have said just to record it for people who can't be here. So we were talking about consistency checks. And we said there was this I check. And this was really for the flat file system, and we checked that each block is used exactly once. And we said if you had a problem where a block was used 0 times, you add it to the free list. If the block was used 2 times on the free list and in a file, then you would take it off the free list, effectively allocating the block. If you had a file that was used twice in 2 files, you would allocate another free block and duplicate that data so each file has its own copy. So the nice thing about this is if you fail somewhere in the middle of creating a file, suppose you're doing something like suppose our code to append to a file looks something like this. Allocate a new block, write the data, write the inode. So if we fail right here, what will we see when we run iCheck? What error, sort of inconsistency, will happen if we fail after we allocate the block off the free list, but before we write any data into it or write the inode? Kosher.
You don't see the block in the free list or in the inode list?
Right, so this will be a case of a block that is not being used by anything because it's not on the free list, it's not part of the file yet, we didn't write this, and so we will just free the block again when we run iCheck. So suppose we do things in a different order, which is in this order. Write the inode, write the data that the inode refers to, and then update the free list, allocate the block. If we fail here, what error will we see? Assuming if we run iCheck right after this point, what error will we see? Right, so if we run iCheck immediately, we will see that this block that we've added to the inode is still on the free list. And so we would repair it by taking it off of the free list and leaving it in the block. If we didn't run iCheck right away and we rebooted and we ran for a while, what we would see is that this inode that we're using here would be used by another file. Then we would see the same block being in use by 2 different files, and then we'd run into the situation where we need to duplicate the block and make 2 copies of it. So, one thing this leads to is, we talked about this a few weeks ago, is what is the order in which the file system should do operations? Clearly, if we do operations in this order, the failure we get is pretty benign, right? We lose a block of data, you don't lose any data from your file. You don't really have potential for sort of corrupting your data in any way. You just lost a block that you can recover relatively easily. If you write things in this order, though, then you can actually get corruption because you can get a case where a block that you're using is overwritten by another file when it allocates the same block. So, given this, what should a file system designer do when they write their code? How does this impact how file systems operate? So one thing you would say is, well, really file systems should always do things in this order. They should always write the change to allocate the block, write the data, write the new block in the inode in this order. So because that would make sure you never lose data if you have a crash. Can you think of any reasons why file systems might not do this thing that seems really obviously correct? Yes?
Because since the program needs the inode and data written, that you can deal with the allocation in the background when the program is using the file.
So your idea is that that the allocation is the allocation innocent is critical, and so we can kind of defer recording the allocation until later. We really want to get the data persistent right away because the thing that guarantees that your data is not around is if you don't actually ever write it. So this case, we definitely lost data because we didn't write it. Here, we at least got the data on disk. So that sort of gets to the point. The reason is, the major reason is, remember we talked about disk scheduling and how the operating system wants to order disk requests to minimize seek time, the shortest seek time first, and elevator and all the look algorithm, the scan algorithm. So the problem is the file system might decide we're going to do operations in this order. But the disk schedule then might say, well, if I do it in this order, then I've got to do a lot of seeking. Because think about, in the Unix file system, where these things are. So when you allocate a block, which piece of the disk do you write for allocating a block? You write the supernode, because the linked list of free blocks is part of the supernode. For writing the data, you have to write to the data portion, which is somewhere else on the disk. To write the inode, you need to write to the inode portion, which is someplace else. And so depending on where the disk head is, if you're moving in one direction, it might be better to write it in the opposite order. So you can imagine if you're moving in one direction, if you're doing the scan where you kind of go in and out, you might do it in one direction. Neither of these orders, actually. You might do it one way depending on which direction your disk head is moving. So for that reason, if you do things the right way, it can make creating files very slow. And people really care about disk performance. Any other reasons that you can think of why this might happen? So suppose your code calls create file, write some data to the file, close file. How important is it that the file system write anything to the disk when your program makes those calls? What would happen if the file system just told you, yeah, I created a file, but in fact, everything you did is still in memory? So this, in fact, is what file systems do. It can make writing the files really fast because it doesn't, usually when you create a file, the file system doesn't bother writing it out right away. It just creates the file in memory, allocates the blocks in memory, writes the data in memory, and it tells you, I did everything you asked. But it doesn't actually write it to disk. And this means that instead of spending 20 milliseconds doing this, you can do all of this in 100 microseconds. So this means if you're writing data, it's like 1,000 times faster. What that means, though, is the file system builds up a list of sort of dirty data that it has to write out, like in virtual memory. So it has all these files you've written to and you've created, and they're sitting in memory, and eventually it has to write everything out because you do want to leave your data around. And when it writes it out, it's going to try to sort it nicely and do scan or look or one of these fancy disk scheduling algorithms to make it really fast, and that's going to destroy this order here. And that is why when your disk crashes, you don't only get these kind of failures where you fail to allocate blocks. That's why you get these other kinds of corruption, because it's just so much faster for the case when you didn't crash to allow corruption to happen. So one thing that's happened is if you think about how long it takes to actually run this. So it used to be, when this iCheck was first written, disks were about 20 megabytes. So disks at the time could transfer about 5 megabytes a second. You could read the whole disk in about 4 seconds. And so doing a consistency check on your disk would take about 10 seconds. Nowadays, in a modern server, you might have 100 terabytes of disk attached to a machine. So how long does it take to read in 100 terabytes off disk right now? Anybody estimate? Ten to the sixth?
100 megabytes per second.
Okay, so 100 megabytes per second with 100 terabytes, so about 10 to the 6 seconds. So you could see that actually running this check, if you have 100 terabytes, would take something like 300 hours, I believe. Is that right? 3,600 seconds per hour, 300 times with 1,000,000 seconds would be at 300 hours. And so running this consistency check on a lot of storage is just incredibly slow. So it used to be every single time you rebooted if your system crashed, when you reboot, Linux, for example, would automatically run this consistency check. We had this problem in our department. We were running a mail server with something like 50 terabytes of storage. It crashed, and it took 5 hours coming up. It wasn't quite as big, to actually just do the consistency check to look for problems. And for that reason, because it is so slow, people have been sort of really looking for ways to avoid this kind of consistency problem, to avoid sort of this, the corrupt, sort of any kind of bad corruption happening. It used to be you could afford to do this. Nowadays, not so much. So various companies have been building file systems that sort of ensure this kind of ordering. And we'll talk later about how to pull that off. So the second check is D check. And D check is really checking sort of the hierarchical namespace, the directory tree, to make sure it's consistent. So what are the kinds of things we can have? One check is, does the number of links in directories, so does the number of times that an inode shows up in different directories equal the link count in the inode? Because the inode is supposed to have a counter of how many different directories this file shows up in. So we can anytime we have sort of redundant information that we can calculate and store, we can compare those. The other big one is, do child directories have a ... entry that point to the parent directory? And if it points to some other directory, then we can sort of think about how to fix it. So very similarly, to do this, you sort of read in all the directories, you read in all the inodes, you keep track of how many times each inode shows up, you keep counters for all these things, and you can then verify this. So if you have problems here, how can we fix this? So suppose we have a file that has a link count of 2. We only find it in one directory. This is a very easy repair. You just change the link count from 2 to 1. If we have a directory that appears to be the child that has the wrong parent, again, we can fix this. So if we have so suppose we have B thinks that its children are A and C, but A thinks its parent is C. When we fix this, we can do two things. We can either say A is correct and rebuild it like this, and say, A is a child of C, and C is the parent of A. Or we can change it this way and have A become the child of B and sort of match that up. So there's not always a clear answer. So what happens if we have a child that has a link count of 1, or directory with a link count of 1, but doesn't show up in any files or directory, that doesn't show up in any directory? So this would mean we have sort of some file over here, and none of the directories in the system refer to this inode. And we think the inode's been allocated. It's not on any kind of free list of inodes. So what should we do in this case? So this is similar to sort of having blocks that are not on the free list that are out there. Yes?
Well, you should definitely put it somewhere.
Right? So so, I mean, the options are either delete the file because it has no name, or not delete the file. And I think we can all agree deleting the file is probably a bad idea, because of the off chance it has something useful, you might not want to lose that data. So you now have a file that has no name and you don't know where to put it. So most file systems have a folder for this. There's like a recovered items folder, I think. I forget. I don't know what it's called on my Mac, but on Windows, for example, there is a folder under the root directory under C: or D:, where the file system checker puts files that have no name. So if you lose a file because of a crash, you can go look in this. I think it's called recovered files, maybe. And you can go, this is where files that have no name are put. And same with directories. Directories that are not the child of any other directory are put into this recovered files folder. And then you can check it periodically to see if anything you cared about actually was lost and recovered in this place. I have actually never ever found anything there. In my case, it's almost always temporary files from Microsoft Office products that end up there. Okay, so any questions on iCheck and dcheck? So, by the way, the name, sort of the program this gets put under on Unix systems is FSCK, the file system checker. On Windows and Microsoft systems, it's called CheckDisk. In Apple products, there's a disk utility you can run that runs this program under the covers. And as you can tell, there is a separate implementation of the checker for every different file system out there, because you have to know what data structures the file system uses to verify that they're correct. So whenever somebody writes a file system, they also write a file system checker to go with it. As a matter of fact, there's a company called SGI, which I don't think exists anymore. They wrote a file system called XFS. And XFS was supposed to be super duper reliable, and it did a really good job ordering all these writes here, and they thought corruption could never ever happen. So when they released the file system, they did not write an FS checker. And it took about 2 weeks before their users started complaining that we really need a file system checker. Even though the file system they sort of guaranteed would never lose data when your system crashes. Any guesses as to why the users needed it? Koshe.
Losing blocks because you allocated them but you never used them or something?
No, they were very careful to even handle this case up here of like allocating a block and not using it. So they didn't have a case where you could lose a block the way they built the file system. Yes?
Your disk fails.
Right. So the problem was their file system was perfect if the disk was perfect. If your disk could ever corrupt something, for example, the head of the free list, you know, there's some place you're storing your free list, you corrupt the data saying where your free list is, it's very hard to figure out what blocks are free and ever allocate another block. So when your disk fails, you still need to go patch things up. And so they very quickly, well, not that quickly, they ended up having to write in a file system checker even for their perfect file system. So Sun, since then, has wrote their own a new file system called ZFS, the Zettabyte file system, which is supposed to be a whole new design, perfectly reliable, similar properties. And their approach to this is every single piece of metadata, the inodes, the superblock, is written 3 times at different places in the disk, and it is also checksummed. And so they basically, if you lose any block on the disk, you still have 2 more copies of that block, and so you won't actually, in different places, so you won't actually lose data. So they hope. Okay, so this ends our discussion of the Unix file system, and I now want to move on to why it sucks, or why we don't use it anymore. Okay, so when we talked about disks, we talked a lot about how locality matters for disks. If you can do sequential I/O, or you can seek small distances, your performance is much better. When we started talking about file systems, I stopped talking about locality altogether. Right? Nowhere in the Unix file system did I say anything about sequential access. I did say there's random access when you're doing these operations. And this is a key problem with the Unix file system. So it will basically put things all over the disk. So just as a quick example, and I just brought this up, this is sort of the core organization of the disk. Your superblock, your inodes, your metadata, your actual data field. One of the things people observed in the 10 years after Unix was created, that most files are very small files on the order of 8 kilobytes or something like that. If you think about the access pattern for writing to an 8 kilobyte file, what you see is, you have to write to the superblock to allocate blocks, you have to write to the inode, you have to write to the data. So every time you're creating a file, you have to seek all the way across the disk and write in 3 different places. And this is particularly a problem because lots of your files are small, so you don't even get to spend a lot of time in the data portion. This is the one place where if you're writing a large file, you could hope to lay things out sequentially and do nice, efficient, fast sequential I/O. But because most files are small, you don't actually get to do that very much. The other thing people observed is that, you know, I said writes are bad. Reads are not so bad. When you're reading, you don't have to read the super block. You do have to read the inode, but if your file is big, the direct block, the indirect blocks are in the data portion. They're just normal data blocks that hold block pointers. So when you're reading things, you have some hope of having locality on disk. But what people observed is that most of the traffic is actually writes. They found that something like 60 to 70% of the accesses to the disk are for writing data instead of reading data, which is surprising. When I measure on my laptop, I see or my desktop computer, I see exactly the same thing. 60 to 70% of the accesses are for writing data instead of reading. Any thoughts as to why this is? Yeah.
Because all the read data is cached.
Exactly. So what happens is when you read a file, it's in memory. And when you read it again, it's already in memory. You don't have to go back to disk. Memories are so big now. I mean, I have 4 gigabytes right here, that most of the things I use, my home directory, you know, my shell scripts and things like that, are all already cached in memory. And so I don't have to go to disk. But when you write data, you sort of actually need to write it out. Because when you write data, you're saying, I want to save this. The write data traffic still has to go at the disk. And so this means that this fact that the things are really spread out is really painful, because most of what you're doing are these operations that are very spread out. So I mentioned the other thing they found was that a large fraction of files are deleted within 30 seconds in Unix. And the reason for this is that a really common pattern in Unix is to create a temporary file, use the temporary file, and then delete it right away. For example, when you run a compiler to compile your code, the compiler internally typically has 2 or 3 passes. So it'll run a pass through to parse your code. The preprocessor runs through. It produces an output file that has a temporary file. It then invokes the first pass of the compiler that reads in that preprocessed file and writes out an intermediate file, which invokes the second pass of the compiler, which reads in that intermediate file and writes out the .o file. So there's lots and lots of short-lived files as a way of doing inter-process communication, because it's just sort of difficult to use pipes. And these files are typically deleted automatically when the compiler finishes. So what happens is if you actually write all these files out, you're spending most of your time, or a lot of your time, writing out small files that are deleted right away. So you have to write to the disk to create the file, and write to the disk to delete the file. So all of these things make the Unix file system perform really poorly. And when there was a group at Berkeley that was porting Unix to the VAX mini computer in the 1980s, this guy Bill Joy, who then went to Sun Microsystems, worked there, and they observed that the original Unix file system gave you about 2 to 5% of your disk bandwidth. So if you had a disk that could do 10 megabytes per second, typically, when you used it for a year, you'd get like 100 kilobytes per second or 200 kilobytes per second access out of it because of these patterns. And I guess, so, I guess sort of a fifth problem, perhaps, to put in here is that the original Unix file system just used a linked list to maintain the list of free blocks. Whenever you needed a block, you take the head off the list. Whenever you freed a block, you push it back onto the list. So when you have an empty disk and you start allocating, things are great. Every time you get a free block, all the blocks are put on the free list in order. Whenever you get a block just next to the previous block. But when you run for a year, what happens is that the free list basically becomes totally random, because you've allocated files, you've freed files, you've pushed those new files back at the head, and so you end up with a sort of totally random set of files. So if you allocate a big file with 100 blocks, you're likely to have 100 blocks spread across the disk. So even if you're doing sequential I/O in your program, reading 100 blocks, writing 100 blocks, the disk has to seek 100 times to access it. So these are all problems that the Unix file system had, and this Berkeley team set out to solve it, and they wrote what became called the fast file system. And the fast file system was in use until about 10 years ago, maybe 8 years ago. So it lasted from 1983 to around 2005, about 20 years it's been in use. The big goals for the fast file system mostly is to fix these problems. And the key thing they want to do is leverage locality. That's sort of the key. Their big idea is we're going to think about which blocks should be near other blocks. So one of the things they had to solve is, how do we decide which blocks should be near each other? Right? So we know if we put blocks next to each other on disk, then we can read them very quickly. If they're next to each other, right next to each other in a track, then we can read them very quickly. If they're on the same track, it's pretty quick. If they're on neighboring tracks, it's kind of quick. But if they're on tracks that are really far apart, it's really slow. So we have various different degrees of closeness. We want to decide, how do we decide what to put close together? Now, an easy thing is we say we want everything close together, right? Because, if you read one file and another file, you'd like them nearby. So the challenge is we also have to say what can be far apart, because we can't put everything nearby. So in thinking about accessing files, can you think of what kinds of things you want to put near each other? And what kind of things don't have to be nearby? Any suggestions? So I will start it off with the obvious answer, which is we would really like all the blocks in a file to be laid out sequentially on a track, right? So you can just read a whole track and it's all the data in one file. This would make reading a file use the full bandwidth of the disk. So that's easy. So what else would we like to keep nearby? What other kinds of things?
Files of the same type, because if you're going to be using data between files, they're probably going to be the same type.
Okay, so I think it's a good idea. The problem is I have something like 10,000 JPEGs constituting 30 or 50 gigabytes on my hard disk. So you can have an unbounded number of files of a single type. So I think it's a good idea, but it's hard to do that in practice. As another example, I have the whole Linux source code, which is 5 million lines of C code. Right? They're all .c files, so they're all the same type, but I typically don't work with all of them. And so what we need are things that are likely to, so we need things that are likely to be accessed together, but there's a small enough set we can actually fit them together. So that's a good idea, but it's not a small enough set. Yes. Okay, and why? Great. So if you think about how, people work, people logically put related things into a directory. So if they have a lot of C files they're working on and compiling, they'll put all those C files in one directory. Like you probably keep all the code for your project in one directory. So when you're compiling, the files that you're accessing are all in one directory. Similarly, a lot of things that people do, older people perhaps, are things like grep star.c, which means look for all the files in a directory ending in C. And so it's very often to do operations on a whole directory. So this is a great idea to keep files within a directory together. Other things we might want to keep close. Yes?
Data that's pointer links to between directories. You have
No, I think you're onto something. So what we want to do, I think what you might be, the way I'll interpret what you're thinking, which may or may not be correct, is that we would like to keep the metadata about a file near a file. If you think when you open a file, you have to read the inode and then read the data. In this layout, you have to go here to read the inode, do a long seek to read the data. We'd like to put the inode for a file near the file data. So we'd like to have the metadata and what it's describing nearby. Yes?
I feel like temporal locality would go hand in hand with this, so if you make a file within a relatively close amount of time, then you should keep it next to each other.
Okay. Okay. So the next question is, we also have to know what can we say do not have to be nearby. We have a whole disk to fill. How do we know when we can seek someplace else to put data?
Maybe when two different programs are writing to a file, they don't necessarily need to be here. So like if you have like our program running and then at the same time you have something else that's running in the background that needs files, they don't necessarily need those files.
So when the files are totally unrelated,
yeah,
we can put them in different places. So the question is, how can we tell when you, so basically when you create a file, we have to decide where to put it. How can we tell when you create a file where to put it? So we could say, for example, we're going to look at the process that calls open file or create file, and we're going to try to say all the things that a process calls open on, or create every file that a single process creates should be nearby, but different processes can be in different places. Okay. Files from different processes, yes.
The actual program and the data it's creating, because you're generally going to load the program
Okay.
memory.
So if you think, that's a great idea. If you think about where those files are in your file system, you notice that typically the programs are kept in one place under /bin or /user_bin, and your data is kept someplace else under /home/ or user/ your username or something. So a typical thing people do is they will say files in different directories. We said files within a directory should be nearby, but they'll say files in different directories can be different places. And this kind of subsumes, in a way, the files from different processes. If your processes are working in different directories, those directories can be in different places. And if your data and your program are in different directories, they can be in different places. So this addresses sort of some things. So what about large files? You know, if we have a file that is a gigabyte or something, it's too big to keep in one place. So how do we, we said we want to keep all the blocks within a file in one place, though. How do we reconcile this? Yes?
We break it into reasonably sized chunks.
Okay.
Try to keep them.
So I'm writing break large files down here. So how big should those chunks be? So, I mean, I think this is a great idea. Take big files, break them into chunks. But we have to know, is the chunk 50K? Is it 100 megabytes? How would we figure this out? Yes?
You could set it to be like the size of a track.
So one track would be a nice size, because if it's one track, you can sort of read the whole, it's sort of the maximum data you can read at the least cost. The challenge is, it turns out that in modern, I mean, this was the era when you could do that. In modern disks, you don't know, the tracks change sizes because of this zoned recording where the outer tracks have more data than the inner tracks, and the disk doesn't tell you what the track size is. You don't even know which block is the start of a track. There was a whole research project of trying to reverse engineer where the tracks were and how big they were, called track-aligned extents. So that would definitely make sense. Other suggestions on how to address this?
The amount of data can be read during the time of a random access.
Okay, so that's another good way, is to say, what we want ultimately, the whole reason we're doing this is to get efficiency. So if we can read enough data sequentially that the cost of seeking is a small fraction of our total time, then it's okay to seek. So what it says is we'd like to have enough data locally. We'd like to have, suppose that we would like to read, spend as much more time reading sequentially than we do seeking randomly. So we'd like to have the amount of data you can read sequentially in a couple of milliseconds, so that when we seek, we're not spending all our time seeking. So whatever you can read in a couple of milliseconds, which at this point would be a couple of megabytes, would be the right amount to have locally. So you read a couple megabytes, it takes a millisecond or two, you then spend a millisecond or two seeking, and you're spending at least half your time reading sequentially instead of seeking. So that's a reasonable way to do it. Okay, so start talking about how FFS solved this. So the first thing they did is they said, we need a way, an abstract notion of locality within a disk. We need a way to say there's some set of things that are nearby and things that are not far apart. And they came up with what they call a cylinder group. And a cylinder group, if you remember this picture I drew of a stack of disks, if we have the same track on each of these, this forms a cylinder. And a cylinder group is really, instead of a single cylinder, it is really a set of cylinders that are nearby. So you might have 10 tracks or 20 tracks on each surface in your stack of disks. And the idea is that the seat cost within a cylinder group is very low, which means that if you put a file and its inode in the cylinder group, you're not going to spend a lot of time seeking between them. If you put all the data within a cylinder group, it'll be relatively efficient. But if you put things in different cylinder groups, they'll be far apart. So FFS carves up the disk into a number of cylinder groups, depending on how big the disk is, and then it tries to reason about what goes in the same cylinder group and what goes in different cylinder groups. So the basic policies So one policy is the one we suggested up there, which is that inodes and the files they describe go in the same cylinder group. I think they said something like the first 64 kilobytes of file data goes in a cylinder group. And after the first 64 KB, we might switch to another cylinder group. And then we will switch, after that, every megabyte or two. So the idea is we want to have it's more important to have all the files from a directory in a cylinder group than to have all the data from a large file in a cylinder group. So that's why they'll sort of switch cylinder groups pretty quickly. And so the last policy was that all the files in a directory are tried to go in the same cylinder group. So these are the basic layout policies. So one of the things you might recognize is if you care about where you put things, you actually need to both worry about where you put data, but where you also have free space. Because if you don't have any free space, you don't have a choice of where to put things. So FFS would reserve 10% of the disk that couldn't be filled up to make sure it had free space sort of spread throughout the disk. That you couldn't sort of totally fill your disk up because then you can't preserve locality. This was overridable by root or by the operating system itself. So normal users couldn't create files once the disk was 90% full. But a super user could come in and fix things. Okay. So the second thing is, if we have these cylinder groups, actually, since it's 2:10 right now, we will stop here rather than launching into anything else. So you know about cylinder groups, and we'll pick up with sort of how these ideas develop tomorrow. So as usual, I have office hours now.